Hello, and welcome to today's webinar on building artificial intelligence-enabled computational storage systems with application processor IP. My name is Scott Durant, and I have a few brief announcements before we begin. First, you can participate in our question and answer session by submitting questions at any time during the webinar. Just type your question into the Q&A text area and then click the Send button. Please note that we'll answer as many questions as we can at the end of today's webinar. But if we're not able to get to your question today, someone will get back to you after the program is over. At the end of the Q&A session, a form will pop up with a brief survey. Your feedback will provide us with valuable information on how we can improve future events. And finally, if you experience any technical issues with the webinar, please type your issue into the Q&A text area, and we'll be glad to offer one-on-one assistance. Today's presenters are Rich Collins and myself. Rich is a Director of Product Marketing for DesignWare ARC Processor IP at Synopsys, and I'm the Data Center and High Performance Computing Strategic Marketing Manager at Synopsys. In this webinar, we'll look briefly at the drivers of data growth and their impact on the storage market. We'll then discuss how computational storage can improve data center efficiency and performance. We'll introduce the key elements of computational storage SoCs and the data flows through computational storage drives, or CSDs, to request and retrieve data. We'll present the Synopsys DesignWare ARC processor IP that can be used to develop flexible, scalable CSDs, and we'll explain how artificial intelligence technology can be applied to computational storage systems to maximize the effectiveness and the efficiency of these systems. We'll then wrap up with a summary and question and answer session. Market research firm IDC has forecast that we'll see a very rapid increase in the rate of data creation over the next few years to 175 zettabytes by 2025. This growth is driven by a variety of data-intensive applications and devices, including the Internet of Things, as we see more and more devices connected to the Internet for control systems, for automation and robotics, manufacturing, and a variety of other applications. In addition, streaming video for applications like entertainment and online education and collaboration, for automation and monitoring and surveillance, is also driving a rapid increase in the amount of data that's generated. Social media, advanced modeling and simulation, medical imaging, and other data-intensive applications are also driving data growth. And as we see this growth, it's resulting in a need for increasing the amount of storage capacity to hold all of this data. In addition, efficient and high-performance data center infrastructure is necessary to be able to store and retrieve data effectively. And of course, along with that, faster interfaces, both at the network level as well as in the chip level, are needed to move data between devices. And finally, in order to extract value and meaning from all of this additional data, we have to have more compute resources to process that data. Cloud service providers, as we see this data growth, are looking to increase storage spending in order to facilitate management of the increased data at a rate of about 25% annually over the next few years. That translates to about $85 billion next year, growing up to nearly $300 billion by 2027. But at the same time, they're increasing the data storage. They want to reduce energy expenses and the carbon footprint associated with their operations. In order to do that, they're focusing their investments on higher performance and lower power compute capability, reducing data movement because data movement itself is a somewhat energy-intensive process. And to do that, they're looking to cache coherent interfaces and, of course, computational storage, which is what we wanted to focus on in this discussion. And at the same time, implementing lower power storage solutions is also very important. I think an interesting data point is that from YouTube, where they're telling us that every minute, over 500 hours of content are uploaded to the YouTube service. And this, of course, is just one of many examples of data-intensive applications and services that are driving growth in the storage industry. It's expected, in fact, that SSD flash capacity shipments are going to grow at over 30% per year for the next 5 years or more. And with this growth, it creates a lot of opportunity in the storage market for those who are suppliers in this market and who choose to invest in leadership in this space. I mentioned earlier that cloud service providers and other data center operators are investing in solutions that reduce data movement requirements. I'd like to take a quick look at a model of what data movement looks like within the data center. As we see data growth, imagine a rack that has at the bottom of that rack a number of data storage servers. In the middle of the rack, there are compute servers that are used to process the data, and at the top of the rack, a network switch that enables movement of data back and forth between storage and compute servers, as well as with external devices. As data quantities grow, you have to add additional storage capacity to the infrastructure. So we represent that here with another storage server. Well, we have now additional data that has to be moved that requires additional network bandwidth. And in order to process that data, you have to have additional compute capability. So the data growth is requiring not just additional storage, but the networking and compute capability to go with that. And as data continues to grow, we continue to have to build out the infrastructure with more and more systems. And this is true unless we can improve the efficiency of systems. So I'd like to take a look at a quick example of a database server or database solution, I guess, that can show us a little bit more about what this data growth looks like and what an efficiency improvements might look like in this particular application. So I've pulled here for purposes of discussion an excerpt from a database that's developed by the United States Environmental Protection Agency, or the US EPA. They test air quality in hundreds of different cities around the United States every hour to measure the amount of pollutants in the air. This database that they build with this contains millions of records, and it's constantly growing because the data collection is an ongoing process. Now, if, as an example, one were to extract from this database a report of the number of times that the pollutant level exceeded what the EPA considers to be a healthy level. And for purposes of this discussion, I pulled the sulfur dioxide as one pollutant to look at. The EPA considers a healthy level of sulfur dioxide to be below 75 parts per billion. So looking at this, I want to run a report that shows the number of occurrences of sulfur dioxide in excess of 75 parts per billion. Well, it turns out that fewer than 1/1000th of the records in this database, that's less than 1/10 of 1%, contain data of interest. But in order to generate this report in a conventional system, my host server runs a query. It retrieves the database from the storage server SSDs, moves what is probably just a portion of that database, the amount that it can hold in the allocated DRAM associated with that host processor, looks through all of those records, finds the ones of interest, and then goes and gets the next chunk of data and repeats that process until it has looked at the entire database and extracted from those millions of records the thousands that contain information of interest. Now, with a computational storage system, if we replace the solid-state drives in the storage server with computational storage drives that have processing capability built in, then the host server can send a request to the storage server to provide records of interest, and the processors within each of those computational storage drives pre-process the information, find those records that contain reports of pollutants in excess of 75 parts per billion, and returns, instead of millions of records from the database, returns just the thousands of relevant information, relevant records. And the host processor can then do any necessary post-processing and return the report. This consumes much less network bandwidth because we're only sending a small fraction of the database over the network. And it also consumes far fewer host CPU cycles because the host CPU only has to look at the records of interest and not the entire database. Furthermore, in the case of a computational storage drive, as the amount of storage grows, that is the number of drives grow, so does the number of computational processors in the storage devices. And therefore, the processing capability scales along with storage. I mentioned that computational storage reduces energy consumption. There's been a number of studies that show the performance per watt or performance per joule benefits of computational storage. One of those studies looks specifically at a high-performance computing workload, that is a multidimensional FFT benchmark application. And in comparing the performance and energy consumed by that benchmark test running with and without computational storage drives, the finding was that there was a greater than 2x performance improvement and less than 50% of energy consumed using computational storage drives when compared to the same solution run with traditional SSDs. So this illustrates some very significant benefits, both implied benefits that the data movement the reduced data movement saves significant power consumption, and also that the added compute capability from the computational storage devices increase the performance of the application. So we get a reduction in data movement, which improves the latency and network bandwidth consumption of the solution, as well as an improvement in performance. And a couple of side benefits of this, because data largely remains in the drive, you get a higher security solution because less information is exposed over the network. And the computational storage processors can actually be optimized to the specific workload, so that helps to improve performance as well. Now, looking at computational storage architecture for a moment, the Storage Networking Industry Association has defined a few different architectures that can be implemented with computational storage. I've illustrated one of those architectures here in this slide and compared it to a traditional storage solution. In a traditional storage solution, you have a host CPU and memory connected through some fabric to a collection of SSDs that have on the SSD or built into it a controller to manage flash functions, but no application processing capability. And so when you are retrieving, or when the host system is retrieving information from the SSD in this traditional case, it needs to pull the entire database or the entire video file or whatever process type of data it's working on from storage, load that into the host CPU, and then do processing there. In a computational storage architecture, there is added to the drive, which we now call a computational storage drive rather than SSD, it's a CSD. We add an application processor to that drive so that the application processor can manipulate data before sending it to the host. And this, by performing these key operations, which can be data filtering in the case of the database application that we just talked about, it could be encryption, decryption, or a number of other types of functions. But it can manage those and offload that processing from the host. And because it scales with the number of CSDs, it gives us a very flexible and scalable solution. So with that, I will turn it over to Rich Collins, who will go a little bit deeper into the technology behind computational storage and the resources for implementing computational storage drives. Rich?
Great. Thank you, Scott. All right. So to dive down a little bit deeper, looking at the computational storage architecture that Scott just outlined, let's walk through an example of kind of how the data would flow in a typical transaction that you might see. This example is similar to what Scott outlined in terms of the EPA data, where the host would initiate a high-level command, and this command in this case is finding a record that's matching a specific key. So the difference right from the bat of what you would see here is in a normal sort of traditional host request would come into the storage SSD controller and request the data. And as Scott outlined, that might be, huge sums of data that would then be basically, pulled from the SSD to DRAM and then processed by the host processor. In this case, the host sends a simple high-level command, basically asking for, basically a transaction to begin. The next step, then the computational storage processor that's part of the drive, it goes ahead and initiates and analyzes the command from the host and then initiates the read request. That request then gets the computational storage, the storage processor then builds the transfer descriptor, which is then used to dispatch to the appropriate flash channel to acquire the read data from the NAND flash elements. So then on the data side, as that read request from the computational storage processor comes in, the data is then brought in from the NAND flash channels, and then basically is analyzed locally by the computational storage processor. So it basically will analyze the data, look for that key match that it's been requested to look for. If it finds a matching record, then it will actually send that matching record to DDR. That data in DDR is then packaged in the host interface protocol and DMA'd to the host memory, where it can then be processed and used by the host processor itself. Once that's done, the computational storage drive will then send basically a message back to the host processor saying that the transaction is complete, the data is available, or if it went through the whole process and did not find any match in that data, then some sort of error message would go back to the host. So again, to sort of summarize, the amount of data that gets dumped from the local storage or the NAND flash storage to DRAM that then needs to be processed by the host is significantly lower. For example, in Scott's case, 1/1000th of the records actually need to have data, stored in DRAM, and the host processor then can focus on what it needs to look at as opposed to having to parse the entire database. So if we look at kind of what are the considerations for in-storage compute, maybe in sort of the delta from where we are today. Obviously, even in a traditional architecture, SSD architecture, there's some pretty beefy processors in there to be able to manage those accesses. But obviously, if you're putting more computational capabilities into the drive itself, then we need a lot higher processing capability built into the drive. Because these are now sort of a user environment, oftentimes these will run a rich operating system like Linux. The end user needs to have an entire development environment. So they have to have a Linux development environment. They have to be able to access the programming capability of the processors in the drive itself. Looking at the types of applications where you would want to have that additional computational processing capability within the local to the drive itself, you want to look at things like key value offloading, video transcoding, search, which is the example I just talked about, whether that's search for text or whether that's images or video. Image classification, certainly this is important if you start looking at automotive types of applications, ADAS, where object detection and classification is required to be able to process data on the road. Machine learning is an upcoming aspect of local or computational storage drives that we'll talk a little bit more in detail about. And then encryption and compression. So basically, the idea of encrypting or compressing the data to simplify or reduce the amount of data that needs to be basically transported around the system to the host processor. On our side, from the Synopsys perspective, our ARC processor IP is particularly well suited for these types of storage applications for a couple of reasons. We have a very flexible architecture. We have a broad portfolio of processors from sort of low-end 3-stage pipeline processors all the way up to much higher-end 10-stage pipeline processors that are more of an application processor, as well as some of the vision processors, the embedded vision processor that can help with the AI portions that we'll talk about. Our processors are very scalable. So you look at the ability to have support a smaller, more low-power drive that might be a single-core solution, all the way up to, in some cases, quad-core, 8-core, or maybe even more, 12-core types of implementations. We can support those with our processor architecture. All of that needs to be done within a seamless programming model. So you have to have the ability to create an environment that can be easily programmed for that multi-core solution, and it needs to be secure. So by keeping the data within the drive itself, that raises the level of security because there's fewer accesses that can be hacked. So a little bit of some background on one of our cores, the core families that's used quite a bit in storage applications today, and will continue to be used as the market moves toward this computational storage, is our ARC HS4X family. So this is a 10-stage pipeline processor family with the ability to add DSP capability as well. You can see that it's a very efficient core. Using benchmarks like Drystone, it's about 5,400 DMIPS at 1.8 gig. And as I mentioned, the ability to have flexibility or scalability from single core to multi-core is supported with this processor and family. So we have single core versions, we have dual core versions, and we have quad core versions. So one of the unique aspects of it is in the dual core and quad core implementations, everything is kind of built in together. So we're not just throwing 4 cores at a customer. Those 4 cores have basically all the glue logic or interconnect between those cores to handle all of the power management, to handle the message passing, the semaphores that need to go between the cores, the inter-core communication that's outside of the bus structure. That's all handled by the processor itself. And then we have an entire software development platform. So we have a whole set of internal tools, debuggers, simulators, instruction set simulators, cycle accurate simulators, as well as an entire supported Linux environment to make it very easy for our customers to be able to develop applications on these types of processors. Okay, one of the examples or one of the major focal points or selling points for our ARC processors is the ability to extend the architecture. So we have a technology we call Apex or ARC processor extensions, which allow customers to add either custom instructions, or in some cases, customers will take some of their proprietary hardware accelerators and they can bolt them on effectively, leveraging internal aspects of the processor. So we provide access to internal control registers. You can set condition flags, things like that, and effectively build into the processor pipeline itself your custom instructions. And a lot of our customers will use this for all kinds of different acceleration, application acceleration in their different environments. But one example that I put here is typically used in storage, where if I'm trying to run, for instance, a search tree algorithm and I want to optimize that, if you look at kind of how that would be done in terms of straight instructions, it might take 10 instructions or so to be able to do that search tree. By leveraging Apex, and we provide a very simple Verilog-based GUI that customers can use to build these, you can effectively create custom instructions that combine many of the loops that would need to be done for this type of example search algorithm. And in this example, you can get that down to, say, 3 instructions instead of 10. And so by doing that, you're going to see a significant reduction in overall cycle count. In this example, it's cut in half, basically 50% cycle reduction. but the overhead is fairly minimal in terms of area, which obviously translates into power and energy savings. You're only adding, in this example, 5% increase to the core hardware, but you're gaining a significant advantage in terms of cycle count reduction. And so these are the kinds of things that our customers do on a daily basis, and it can have a significant visual impact in the overall application savings itself. So we talked about the HS4X family. That's our 32-bit application cores. As we mentioned, the adding more computational capability inside the drive is rapidly increasing the computational requirement, or the horsepower that the processors that are inside that computational drive need to be able to support. And we recognize that. And so in our next generation, what we call our ARC-V3 architecture, we've extended the processor portfolio to 64-bit processors. So we have single core 64-bit processors, and we've built a cluster around those 64-bit cores that can support up to 12 cores per cluster. And I'll walk through a little bit more detail on the cluster architecture itself. In terms of a little bit of detail on the core, the 64-bit core itself, so we do support up to 16 meg shared cluster cache, and I'll talk about how that can be allocated or partitioned across the multiple cores within the core cluster. From a performance perspective, we have single core performance of 6.1 core mark. And then obviously by supporting a scalable multi-core architecture that can scale to a much higher overall core mark performance rate. And so overall, we see that this kind of a cluster performance for these 64-bit cores is a pretty significant boost over what we can provide with, say, a quad-core HS4X today. Again, as you push more of the external computation beyond just the storage access control into this processor, that you want to have a pretty significant amount of overhead that can support that additional programming capability. As with the HS4X cores, we have the exact same, complete software development environment, all the Linux tools, all the what we call middleware, debuggers, simulators, and whatnot are all available for the 64-bit cores as well. So digging in a little bit on the cluster. So as I mentioned, the processor cluster itself supports from 1 to 12 integrated cores. It's all tied to a coherent interconnect fabric between all of those processors, and you can mix and match, for instance, 32 and 64-bit cores, and I'll talk on the next slide is an example there where within the cluster you can partition different operating systems and different tasks. Everything is part of the low latency, high bandwidth interconnect. So we do support standard interfaces like ACE Lite on the master side, as well as external NOCs, using standard interfaces like AXI and AHB for peripheral access. One of the additional or supporting aspects of the architecture is that we can extend it as well to support up to 16 hardware accelerators. So whether or not you use your own development tools or you have your own hardware accelerators, you can actually build accelerators that have closely coupled memory. That closely coupled memory can then be part of the overall coherent interconnect. So you can actually have easily create examples where data can be stored on the closely coupled memory of one of the connected hardware accelerators, and that data can then be accessed coherently through or by any of the HS processors as part of the cluster. Some other aspects, interesting aspects from a performance perspective, we've dedicated quite a bit of resource to quality service or QoS. So you have the ability within that cluster to effectively steer the data and manage the performance that's required. So if you have, for instance, a partition of 8 cores, and that octa-core implementation needs to have the highest priority in terms of data bandwidth, you can easily steer that and let the other quad cores, for instance, have a lesser role or a more secondary role. So you can easily make sure you manage the performance requirements of the cores in the cluster. I talked about the shared cluster cache and shared memory. So just like anything else with the quality of service and the ability to sort of move things around and partition, you have that ability with the shared cluster cache as well. And so you can partition the shared cache any way you need according to the core partitioning that you need to do. And again, set priorities on which of the cores need to have the highest bandwidth. And then most of the other things are kind of standard interfaces, things like trace and debug. All of those things are supported within the processor cluster. So as kind of a real world example, you could easily create a system like this where some of the cores within the cluster need to run on Linux. And so maybe it's actually managing the NVMe over Fabric interface and all the stacks and the Ethernet drivers and everything that's required there for basically communicating with the host are part of that cluster. And then a second set of cores within the cluster might be running on a different OS, maybe an RTOS, and maybe this is focused on the flash management side of the storage application and all the stacks that need to run on the flash management side. So it's very easily and flexible with our HS6X family to partition these cores within the same cluster, very well. So in this example, you could create a 4 and 4 where I have an 8-core implementation of the cluster where I've allocated 4 cores for each of the portions of the application. Or you could basically bias it, if you have up to 12 cores, so you can bias it however way you need to based on the performance requirements. Or you could dial it all the way back to where all 8 cores are used just for flash management, going back to kind of a more traditional SSD implementation where, all 8 cores can be used just for flash management in a simpler architecture. So sort of shifting gears and to talk a little bit more about AI. So I think most people are probably aware of kind of the concept of AI, but just kind of reiterate here, the whole concept is to sort of take what's traditionally seen in brain functionality and neurons, translate that into kind of mathematical functions, and then create specialized hardware accelerators called neural network engines that can then process data in this way. So it's kind of a better way to manage the types of data that AI applications are going to look at, where you need to characterize data, you need to create training models, and then you basically need to program the processor and then sort of adjust that real time on the fly as needed, sort of local inference, if you will. That's kind of the common, high-level definition of what's required in any AI application. But in storage, why would you apply any of those sort of AI algorithms in storage? For one, a lot of the data is being created at the edge, and so being able to apply some of those AI techniques at the edge is becoming increasingly important. It's expensive to move the data, so the whole point of this computational storage, the large point, is that you want to reduce the amount of data movements, and so you can do things more locally, then you're reducing the amount of data that needs to be moved around. And basically, you can then apply these algorithms, and I'll talk a little bit about some of the examples of where you would, the types of things you would want to do with AI. But basically, you can effectively isolate to where the AI processing is done offline within the local storage, and then only have to move the data that's needed to either the host or basically within the data center. So this is becoming increasingly more prevalent in the industry. So what are the kinds of things that you might apply AI algorithms to in storage? Things like predicting hot and cold data, trying to determine where things should be stored in data locally based on required access. So obviously, if you have a wide, vast array of SSDs, having things closer that are used more often is going to be important. Overall data lifecycle management of the data, and then be able to uncover insights. So what kind of analysis can you do on the data? You can do that locally. Object detection and classification, like I talked about the example in ADAS, where you want to have the ability to detect objects and recognize them and classify them is critical for those types of applications. Storage tiering is another thing. So if you look at a kind of an overall implementation, it's usually not one size fits all. Usually you have a little bit of a hodgepodge of architectures, different kinds of storage that balance speed and cost. And so having some algorithms that can sort of intelligently try to figure out where the data makes most sense to store based on when it's going to be used and how it's going to be used. That's another aspect where AI algorithms can be particularly helpful. And then just overall improving the SSD performance and the quality of service. So extending the life, improving the reliability of the SSDs, lowering the write amplification factor or WAF, so that basically the data that you do analyze and process becomes more useful. So you're actually doing more processing on actual data versus sort of blind accesses. Data clustering, and then basically being able to do some fault prediction on the drives itself, which ties a little bit into the extending the SSD life and improving reliability. The picture there on the right is an example of an engine that we call the embedded vision processor in the Synopsys ARC portfolio, and it's pretty well suited for these exact types of AI applications. There's sort of multiple aspects to any AI engine. One is being able to do sort of basic vector processing, sort of classic DSP, and so we have a built-in vector engine. There's still an amount of scalar or sort of regular RISC types of processing, and so we have a multi-core scalable RISC engine built into this. And then the sort of big picture, or big part of the unique part is the neural network accelerators. And so in our embedded vision product, we've created a very scalable multi-MAC that can go up to basically thousands of MACs to be able to scale depending on the types of performance in the neural network application that's required. But again, this combination of having the vector processor, the scalar processor, the neural network engines, all the interconnect and shared memory, fully supported by tools, again, makes it very easy for customers to be able to develop their AI applications on our portfolio. So to sort of sum things up, we talked a little bit about kind of the transition from the traditional type of storage architecture where the host processor is doing the storage or the request to get the data, say in a read case. The storage controller is effectively creating the transaction and pulling that data and basically dumping it back to DDR for the host to process. As we move toward the more in-storage or computational storage types of architectures, a lot more of what's required to manipulate that data or to use that data is being done locally on the drive itself. And so instead of the host having to get all the data dumped to it and do the analysis, the host can basically put in the request, let the computational drive go off and do its thing, and then send back an indication it's done, or whatever subset of data that the host now needs to analyze or process is available. And so the host has a lot easier job, if you will, or smaller amount of data that it has to work on. So all of that is happening locally. So instead of having to copy data multiple times, the data stays in the drive. It adds a much higher level of security. Again, any types of interfaces that you add, the more interfaces that you have to data, just increases the threat surface effectively. So you've created a lot more opportunity for someone to either physically or through software hacks be able to access that data. So the more data that stays locally within the drive, it's obvious that it becomes a much more secure environment. And then you can really optimize that workload. So we gave that example of if you're doing, searching through gobs of data to find specific patterns and whatnot, you can really spend some time really making that application that runs locally on the drive much more efficient and optimized. And then by having this sort of already pre-processing or bit processing architecture built around the computational drive, adding AI into that drive becomes a much easier task. You basically can you can build that over time. So you have your computational drive, you can add AI elements to it and become much more efficient about how you're processing data. So those are kind of things: latency, bandwidth, lower cost, higher reliability, more secured environment, and ultimately translates into lower power consumption. Those are kind of the big ticket items for why you would want to move toward this type of architecture.
Thank you, Rich. Appreciate the overview. Before we get to questions, I do want to remind everyone to fill out the feedback form after the Q&A session is over. And I want to thank you in advance for providing that feedback. We're now going to move on to the question and answer portion of the event. To participate in the Q&A session, please just type your question into the text box on your screen and click the send button. And if you'll give us just a moment to look through the questions, we'll get started. Okay, it looks like our first question is it okay to mix and match different types of cores in the cluster? Rich, do you want to comment on that?
Sure. Yeah, we've built the architecture such that we have a combination of 32-bit and 64-bit cores, which can be mixed and matched in the cluster. Obviously, leveraging the interconnect and the bandwidth that's afforded by having them all connected as part of the cluster. We also have our external hardware accelerators that I talked about that can also be leveraged for additional compute that can be connected to the internal fabric.
Okay, great. And it looks like the next question is also about something you spoke about, Rich, the Apex acceleration that you talked about. Is that easy to implement, or does that require a deep understanding of the processor pipeline?
No, it's actually really easy to implement. We provide a GUI tool that makes it super simple. It's all Verilog based, so customers can add instructions and validate that they've been added correctly. We then use the tools can then basically use those custom instructions as intrinsics effectively. So it's effectively a seamless ability to add custom instructions to the architecture.
Great, thanks. Got a couple of questions here about timing. One of them, are you seeing computational storage implementations in the data center today? And that's an interesting question. We're certainly seeing a lot of interest in computational storage amongst enterprise IT and other data center vendors. There are right now more than 40 vendors that are participating in the Storage Networking Industry Association's Computational Storage Technical Work Group. They're working to define and agree on the core architectural concepts and principles behind computational storage. So there's much activity in the standards bodies right now. We're also seeing some early deployments by cloud vendors that are rolling out computational storage for edge computing. And in the storage vendor space, we've seen a number of vendors that have delivered some flash drives that have built-in accelerators. One of those is Starblaze, for example. They've got a data center targeted flash drive that has integrated processors for on-device application acceleration. So we're seeing a lot of activity in that space as well. And I think interestingly, Tim Stammers of 451 Research, a market research vendor, has made the statement that computational storage is set to become commonplace. And I really think that we'll see broad adoption of it over the next couple of years. So it is a little bit early right now, but definitely a time when it's time to get ready for this. And another question regarding timing, maybe Rich, you can comment on this. When do we see the inclusion of artificial intelligence in these computational drives becoming mainstream?
Yeah, I would say, we're starting to see it now, certainly with our lead customers and customers that we interact with in the storage market are already starting to look at this. I think, there's quite a bit of IP and, like we talked about with our embedded vision processor that's focused on AI. So combining, sort of standalone or traditional processing with the AI is becoming much more mainstream. So, I would imagine that this is going to roll out with, some sort of the heavy hitters, if you will, in the storage market quicker. But I think you'll see this pretty commonplace within the next 2 or 3 years.
Okay. Great, thanks. And looks like a couple more questions about Apex. One, how does Apex implement the complex in-storage compute instructions, which need to mix compute operations with storage and memory operations?
So Apex, so there's a couple of different things there. I read that is, so Apex is just a mechanism for being able to customize or add custom instructions. And so, there's nothing about the architecture that, you still have to manage your software in terms of building your software architecture, right? So it may not make sense to actually add custom instructions. For example, the example I gave, usually where our customers are adding custom instructions, it's to reduce the overall cycle count of, some loop or some algorithm that's used in the flow. So in other words, instead of having to, you basically can do in a couple of cycles what you would normally do in, say, 10, 15 cycles. So I guess the question is kind of how does that roll in? You are with Apex able to access many of the core functions. So you have access to control and status registers, auxiliary registers within the processor itself. So effectively, you can add those instructions, and they become part of the rolled out instruction flow for that core. And like I said, the tools, the software tools, will look at it as intrinsic. So anything you add as a custom instruction will basically treat it as an intrinsic when you're trying to do your software debug.
Great, thanks, Rich. And a related question, how does Apex compare with other IP like ASIP Designer, which also allows custom instructions and the addition of accelerators?
Yeah, it's a little different. So ASIP Designer is a tool that you can build hardware accelerators, but they're effectively, so there's a couple of different ways that ASIP Designer is used. One is for architectural exploration, where you can build quick and dirty hardware accelerators that you can use to, kind of assess functionality. Other customers use ASIP Designer to build a whole processor. So basically, if you have your own very niche, specific type of architecture where you want to build a core, say a very low power core, low power DSP or something like that, then you can use ASIP Designer, build that processor to effectively build the entire processor. From a hardware accelerator perspective, you can use ASIP Designer to build hardware accelerators, which then can be plugged in to our standalone or our standard ARC cores using Apex, which is kind of what I showed there in that, the architecture for the cluster and the HS6X cores, where customers will build, we've had customers that take a ASIP Designer and build ASIP hardware accelerators with closely coupled memory that then becomes part of the coherent architecture of the cluster, and bolt those on to the HS cluster. So I wouldn't say they're not mutually exclusive types of things. One is a tool that can do a lot of different things, and it can basically be complementary to building accelerators that can use the Apex interface on our standard ARC processors.
Great. One more question here. Can the accelerator on a computational storage drive typically perform just a single function? Or in one of your slides, you had a list of several types of applications that could be accelerated. Can a single accelerator be used to accelerate multiple applications?
I guess that's a question for me.
Yeah, Rich, if you wouldn't mind commenting on that.
Yeah, I guess it's really up to the customer, the user. They can build. Most of our customers build fairly simple operations using Apex, where they'll just use add some custom instructions to optimize an algorithm or a loop. But there's nothing to prevent you from building as complex an accelerator as you need to build. If you have that in your portfolio and you want to basically plug that into the Apex port, then that's certainly something that can be done. It's really up to the end user.
Okay, great. And another Apex question, how hard is it to optimize the software stack around newly added custom Apex instructions to effectively utilize the new instructions in an existing code base?
I would say it's fairly easy, because the sort of cycle for building, it's a quick turnaround, right? So because we have these automated tools, the running through the full cycle of adding instructions and then running, your simulations based on those instructions is fairly straightforward. So, in a very short period of time, you can basically go through and optimize your code. And what we always tell our customers too is our application engineers are always available to help as well. That's something that we do quite often with our customers when they're using Apex to build their custom instructions. Well, oftentimes they'll want some help from our application engineers, and we always provide that help for our customers.
Great. All right. Thanks, Rich. Looks like that's all the questions that we have for today. If nothing else pops up here right away, I would like to point out that if you would like additional information about today's webinar, please feel free to visit synopsys.com/designware-IP. So I'd like to thank everyone for attending the webinar today on building AI-enabled computational storage systems with application processor IP. Remind all of you to please fill out the survey that will pop up in just a moment. And thanks again for joining us. Hope everyone has a great day.